Okay. Last time we were talking about timing, and we kind of transitioned from talking about system level timing to individual circuit delay. And I wanted to continue on that. It's kind of fun. So what we're going to do is look at the derivation of the delay for some basic elements. We actually did the inverter last time. So we had started out here where I showed you a common practice is to model the conductance of the transistors as resistances, and then consider the resistances in conjunction with the various capacitances. And for that, we can understand what the transient response for an inverter is. And of course, it's with this RC type modeling, the transient is exponential. So we have exponentials that when we transition a node from 0 to 1, it's kind of an exponential transition. And when we go from 1 down to 0, it's also kind of an exponential transition. Now, we went into a little more detail about these capacitances. And it turns out for a capacitor, or for the inverter, the first thing we did was consider the transient response for the inverter for its own internal capacitance. So part of the property of logic gates is that they have external capacitance that they're trying to drive. That's the process of sending a signal to other logic gates. But they also have some internal capacitance that they need to overcome in order to change their output. Right? So we looked at that in the case of the inverter has this internal capacitance. And this internal capacitance comes about because when the transistors are laid out, there's a region for the, in this case, the two drain regions of the N-type transistor and the P-type transistor. Those drain regions have some capacitance. Right? So that's what we mean by internal capacitance. Okay. So in this case, we said for traditionally P-type transistors, for a given size, for a given width, have half the conductance or twice the resistance of an N-type transistor of the same width. Right? So in order to make a balanced inverter where it pulls down at the same rate that it pulls up, we have to make the P-type transistors twice as wide. Right? If we make the P-type transistor twice as wide, then its resistance of the pull-up transistor and the pull-down transistor will be the same. However, the P-type will be twice as wide. So the total amount of internal capacitance is there's one part of it that's contributed by the pull-down and two parts that are contributed by the pull-up because the pull-up is twice as wide. So that's where this 3 came from. We said that the internal capacitance is 3W times CD, where CD is kind of the unit capacitance for the drain regions of either a P or an N. So we've got 3 units there, 2 from the P and 1 from the N. So that's where that came from. And we have kind of the unit resistance for the N-type transistor, and we express the resistance of the P and of the N, both in terms of the N, just so we have fewer terms around, right? So that's going to be R over W, because if we made the transistor a width of W, we make it W times wider, the resistance goes down by a factor of W. All right. However, if we make the transistors W times wider, the capacitance on the gate of the transistor, which is represented here, this capacitor out here in this model is the sum of the gate capacitance of the P-type and the N-type. This is the capacitance into the inverter, right? And the capacitance looking into the inverter is the capacitance of the gate of the P and the capacitance of the gate of the N. Since we said the P-types were twice as wide to have a balanced pull down and pull up, again we have 3 units of gate capacitance. 1 units from the N and 2 units from the P. And of course, if we made everything W times wider, we would scale up the input gate capacitance by a factor of W. So that's where we get 3W CG. Okay. The next thing we did then to make the analysis a little cleaner and simpler is we found a way to relate drain capacitance to gate capacitance. All right, just so we have fewer types of capacitors around, and introduce this thing called gamma. And gamma is a factor that relates the capacitance of drain per unit to the capacitance of gate. And it's a number that's process dependent. We'll just keep it as a variable for now, as a little factor, and it's close to 1, right? And later we'll make it be exactly 1, and we can see what happens in that case. So once we do that, then we can re-express the internal capacitance of this inverter as 3W gamma C sub G. Okay, once we did that, we can do some analysis and get to a nice result, and we did get to a nice result at the end of yesterday. Again, we're just looking at internal capacitance here, but if you look at internal capacitance and the associated R's, we know that the delay, the propagation delay to the halfway point is going to be log base 2, a natural log of 2 times RC. The R is either we're pulling down or we're pulling up. It doesn't matter in this case since it's balanced. So that's R sub n over W times the C that it has to charge or discharge. That's the internal capacitance, which we got right here, 3W gamma C sub G. And then you can see the W's cancel out, which says that the intrinsic delay, the delay of this inverter without any load, is independent of the size of the inverter. When I say size of the inverter, I mean the width of the transistors, which is kind of interesting. So we get to this point. All right, this is the, as I said, the intrinsic delay of the inverter. This is the delay of an inverter without any load capacitance. Now, the next thing we did was we now imagine that we have some load capacitance here. I talked about this last time. This C sub L represents everything that this inverter might connect to. Right? So it's capacitance in some wires, capacitance in some other logic gates. All logic gates have input capacitance because you're, in the case of CMOS, we're connecting to the gate terminal of some, usually 2 transistors. Okay, so we can change our formula here. Now we have 0.69, which is natural log of 2, times R sub n over W, which is the pull down or the pull up resistance, times now C internal plus C sub L. Right? So that's going to represent the propagation delay for this inverter if it's driving an output capacitance. Right? And then we can plug in what we know. We know C internal, which is here. Right? And then refactor things, factor that out. We get to this point, and we get to this point, where TP of 0, or TP naught, is the intrinsic delay of the inverter. That's this part here. So the intrinsic delay of the inverter times 1 plus CL over C in with gamma on the bottom. We are going to re-express CL over C in as F. We call that the fan out of the inverter. It's the ratio between the output capacitance, what the inverter is driving, relative to its own its own input capacitance. That's called fan out. So this is a nice clean representation of the delay of the inverter in this case. All right. So we have, if we look at this, this is really kind of a linear formula, which we can think of graphically like this, where if we look at the delay of this device, this inverter, as a function of its fan out, as a function of how much it's driving, how much capacitance it's driving, there's a y-intercept and then a slope. Right? The y-intercept is just the intrinsic delay. That's the delay when fan out is 0. Right? And then as we add more and more output capacitance, the delay will go up and up and up in a linear way. So understanding the delay of an inverter, and we're going to do it for logic gates in a minute, You can see it's just a linear relationship. And this is a consequence of the way that we model transistors as resistors. But it's very close to it's a very close approximation, so this is commonly used. So if you know the intrinsic delay of some logic gate, you know what its fan out is, you'll know what the delay is for that particular logic gate. Okay, so that was just all kind of review from the end of Tuesday. So now, interesting thing, what happens, can we compare how the inverter delay is and how the inverter delay scales with F and what the intrinsic delay of the inverter is compared to, say, a 2-input NAND gate or a 2-input NOR gate, or maybe even an N-input AND gate or an N-input NAND or an N-input NOR. So what we're going to do is derive the formula for the gate propagation as a function of fan out, as we did with the inverter. We're going to do it for this circuit here. That's a little more complicated. I can tell you last semester we had it as a homework problem. And this year I'm going to just present it here in class. We'll have some other kind of homework problem. So we're going to derive the equations based on the input connected to the transistor closest to the output here. So for input A. There's a slight variation depending on which input you choose. We're going to assume that B is set to a 1. It's been at a 1 for a long time. Okay, so that means this node here is at ground. Okay, so it's going to eliminate the need to worry about discharging that internal node. This internal node has some capacitance on it. But we'll just, all I'm saying is we're going to forget about that now. And so, and that's what I'm saying. We're going to forget about these this internal capacitance. Okay. As before, we're going to assume that the resistance of the P-FET is twice of the N-FET, right, for a given width. And so the other thing we want to do is size as we did with the inverter, we're going to size the transistor so the pull down of this gate, pull down strength is the same as a pull up gate. So the pull down transition time is the same as the pull up transition time. Right. Oh, and I think I missed one. Oh, this one. So we can fairly compare to the inverter, size the transistor so that the capacitance of each input is equivalent to the input capacitance of the inverter. Right? Because what we want to do is say, for a given load, what is the output drive of this device, right? We want to compare it in a fair way to the inverter. So we're going to make it look like an inverter as far as what its input capacitance is. Okay, so here's the problem setup, and this is the hardest part, setting up the problem. Once we set it up, then it's just a matter of algebra to get to the right answer. And this takes a little bit of thought. Okay, so to keep the pull-up and the pull-down delays the same, in this case, we keep the transistors all the same width, right? Because look at the configuration of the circuit. We have two N-type transistors in series, right? So those resistances are going to add together. Two transistors in series pulling down. Worst case, single transistor pulling up, right? If the P is twice as strong as the N, if we keep all the transistors the same width, we'll get the same pull down as we do pull up, right? You see that? Because these are twice as strong, but we're putting two in series, and that makes the resistance twice as what it was before. And so that will kind of be equal to a single P-type transistor pulling up with the same width. Right, so the key here is to understand all the transistors for this NAND gate will be the same width. Now, the inverter had an input capacitance of 3 C sub G. Right? That was with the P of the width of the P being twice the width of the N. Right? So the inverter kind of looked like, let's see if I can draw the layout of these transistors to help visualize. So if that was the p-type transistor, it had this maybe 2 times W. And then this was connected somehow down to the n-type transistor, which was going to be was half the width. W. And this gave rise to, and these are connected together. So this gave rise to an input capacitance of 3 G sub C. Now what we're saying in this logic gate, because of the series n-type transistors, all the transistors are the same width, if we didn't do anything, we would end up with an input capacitance of 2 GC, right, instead of 3, as we did with the inverter. So to get the input capacitance to equal that of an inverter, we have to increase the widths by 3/2 of both the transistors here. Then we're going to have 3/2 plus 3/2 will be equal 3, right? If we increase the width by 3/2, that means the resistance changes by 2/3, right? Because the resistance goes with 1 over the width. Right, so we get to this configuration. So this is the assignment. This is the resistive values. Right. So we have 3GC looking in, or 3CG looking in at the input. The p-type transistors now are shown here. The resistance of the p's are here, and the resistance of the n's are here. Now, is this the right? Yeah, this is the right one. The we said we increased the widths of the n-type transistors, all the transistors, by 3/2. That means their resistance is 2/3 R. Right. The p-type transistors are, for a given size, and we said they're all the same size, is twice as resistive. So if this is 2/3, each one of those is going to be 4/3, twice as much resistance. All right. So we have those, and everything's expressed as in terms of R sub n. Right. There's the internal capacitance again, and there's the load capacitance. So now we have everything we need in order to solve this. So that's this page here. There's a bunch of algebra. But here, the first thing is to figure out what the internal capacitance is. That's going to be the capacitance due to this drain, that drain, and this drain. Right? So it's 2/3, sorry, and remember now you have to keep in mind the widths. They're all the same width, and the width is 3/2 W. Remember we said we increased all the widths by 3/2, which was back here. I probably should have marked this on here so you can remember it, but here it is. So this is 3/2 W, and that's this one, 3/2 CD. And then there's these two are also 3/2. You put two of those together, you get 6/2 CD. So the total internal capacitance is 9/2 CD. So that goes in here, along with gamma and the W and the CG. To put it in terms of CG, we leave CL as CL. And then the resistance of the pull down or the pull up is the same. It's 4RN over 3W, right? It's either one of those or these two in series. It's the same number, 4/3 RN and a W. And so we put that in, and then we kind of do sort of what we did before. We factor, and we eventually can get it down into this form here. Right? So now we have tau sub P naught. This is the same intrinsic delay that we had before, that we had derived previously for the inverter. If you look, it's right here. But then it's times this thing, which is 2 plus 4/3 F over gamma. What was the inverter? The inverter was 1 plus, it was F over gamma, right? That was that straight line I showed before. So what this says is this NAND gate for a given input capacitance has twice the intrinsic delay. That's the delay with no load. And it has a slope that's steeper than the inverter, so it's more sensitive to output capacitance. The delay grows faster as we add output capacitance than it does for an inverter. And that kind of makes sense because we have transistors in series here, and in the inverter it's just a single transistor. So this is going to be less efficient somehow in its ability to turn input capacitance into output drive. Okay, so that's the result for the NAND gate. We can do a similar thing for a NOR gate. In this case, the P-type transistors are in series. Plus, they're twice as weak in a traditional process, right? So what that means is we have to make them, to kind of balance them to a single N-type transistor, we have to make them 4 times as wide. We need to make them twice as wide because we're going to put 2 in series, and we need to make them another 2 times wider because they're intrinsically less conductive than the N-type transistors. So the width of the P is 4 times the width of the N. Right. And then we have to adjust their sizes in an absolute sense in order to get this 3GC here. So that's the fair comparison to the inverter. Right. And that will likewise affect the resistances. And this is without going through all those details. This is how it ends up. These end up being, the resistance here is 5/3 R. The resistance here is 5/6 R. Right? And remember, these are 4 times as wide. If you do that, then again, figuring out what all the capacitance is at this node, the output node, due to the drains of these devices is shown here, the calculation. So it's 2 times these. These 2 are 3/5, and then that's supposed to be a parenthesis there. And then the pull-up is 12/5 CD, and you get 18/5 C sub D. And we plug that into our same kind of formula. It's just an RC formula, but where C is internal plus the load. Again, we do some rearranging and factoring, and we get down to this point here, where for the NOR gate, the intrinsic delay is the same as it was, interestingly, for the 2-input NAND gate. It's a 2, but the slope is different. It's 5/3 here, which is even steeper. So this is even more sensitive to output capacitance, meaning for a given output capacitance, this gate will be slower than the NAND gate. We can summarize that here. So this was our inverter before. Has this intrinsic delay, which is 1. We have twice the intrinsic delay for these 2 input gates. And the slope of the NOR gate is, both of the slopes are higher than for the inverter, and the slope of the NOR gate is even higher than that of the NAND gate. So in some sense, the NAND gate is less efficient of the 2 input gates. So this goes back to what I said earlier in the semester, that in CMOS we tend to favor NANDs, because at least for traditional CMOS processes where the P's are weaker, if you have to put transistors in series, put the ones in series that are the most conductive, and those are the N-type transistors. The P's are already weak, and you put those in series, you're making the pull-up even weaker. So the transistors have to get wider, but by making the transistors wider, then you have more input capacitance, which then slows down the previous stage, right? So the whole thing is much more efficient if you do it with NANDs, and it's because of the slope here. Okay, so what about gates with more than 2 inputs? I'm not going to torture you with going through the math for that. Maybe we'll ask you for homework, but if you set it up and go through the same analysis, for a 4-input NAND gate, you end up with the intrinsic delay of, for the inverter, same one we've been using, the TP naught. But now the intercept is 4 and the slope is 2. So that would be up here, would have even a higher intrinsic delay and even a steeper slope. Right? So it gets particularly bad as you add more inputs to logic gates. I forgot how it generalizes. This might actually be the number of inputs. I think it is. In general, that maybe represents the number of inputs. Okay, so that's one way to think about gate delay and analysis of the difference between different logic gates. And also, you should understand that there's a nice linear model here for the way we model the delay of individual gates. Yes?
So here you were calculating delay for a 4-input NAND.
Yeah.
If you were to instead construct a 4-input NAND by like building the circuit like as a hierarchically.
Yeah, or a cascade of 2-input NANDs. Yeah.
Yeah. Do you get better?
I don't know. I was thinking of having that be a homework problem where you compare that to. So how do you make a 4-input NAND? So does that give us NAND? I think NAND NOR is what you need in order to get something. I think it's that. So interesting question. I don't know the answer. It's probably somewhat technology dependent, but how would the delay of that compare to the delay of that? I think that would be a good homework problem. And you could do it algebraically, or you could do it with SPICE and compare them. So maybe we'll do that. Okay. Any other questions on the gate delay stuff? Oh, and by the way, it's clearly, if you went to more inputs, it's rare to see NAND gates with more than 4 inputs because at some point it's obvious that this type of circuit, a cascade of smaller, lower input gates, has less delay. It's for several reasons. One of them is this reason, this slope thing. The other is that I didn't talk about it much, but if you look at the pull down then in these high input gates, you end up with a lot of transistors in series, like this. And if you think of each transistor as a resistor, and there's a capacitor at each point here, because each drain region and source region has some capacitance. So what we have is this long RC structure. We looked at that with wires, and I showed you that. In fact, worst case, this has a delay that's proportional to the square of the number of elements here, right? Because if these are all charged up to a 1, let's say there are all 1s everywhere in here, and you turn all these things on, well, you've got to discharge this C through that R, and that C through 2R, and that C through 3R, and that C through 4R. And again, you get this 1 plus 2 plus 3 plus 4, which is like a squared. So the other thing about high input logic gates is you have long strings of transistors, and that tends to be slow. And so there's another term, kind of an exponential term that comes into this. It's not even linear anymore. And so it gets worse than what I told you here. All right, so we tend to favor logic gates with a relatively small number of inputs. Okay, any other questions on that? Okay, so I'm gonna, so this story, we've been talking about logic gate delay, and I'm gonna complicate the story again a little bit with wires. We talked about wires the other day and said that they have some delay, as I just said a minute ago, that grows proportionally with the square of the length of the wire. And that's because the wires that if they're long enough that we need to consider their resistance, then we kind of model it this way, as the distributed sections of R and C. As I said the other day, very short wires, the resistance of the wire is relatively small compared to the resistance of the transistors that's driving it. So we just ignore that resistance and think of the wire as nothing but a capacitance, which contributes to the load capacitance of the logic gate. But there are cases when we need to consider both. It's always there. The resistance is always there. It's not that it doesn't factor in, it just factors into a very small percentage. So our approximate models can ignore it. Now, I told you the other day that the delay to drive a signal across a wire is proportional to the unit resistance and times the unit capacitance times the length of the wire squared, where this is ohms per, let's say, micron, and this is capacitance per micron of length, and that's the length in microns squared. But I said this is proportional. If we want to look at what the actual number is, I've shown it down here. The delay is around half of what it would be if the R and the C were lumped together. So if we put all the resistance at one side and put all the capacitance at another side, right, then we'd have an RC constant associated with that. But that would be inaccurate because it's actually distributed, right? And so instead of being a normal RC, it's about half of a normal RC, right? Because it's all spread out. And in fact, it's not exactly half. It's 0.38 turns out to be the number if you actually solve the equations. So the propagation delay for just the wire with its self-loading is 0.38 times the unit resistance times the unit capacitance times the length squared. Okay, so that's something we're going to need in a minute. That's why I thought I'd tell you that. So what happens then if we drive a long wire with a logic gate? And so this is kind of a prototypical situation here where we have a logic gate. For now, we just talk about an inverter, but we could do it with NANDs and NORs if we wanted to. We have a long wire here, and then we're driving some other logic gate or collection of logic gates at the other side. So at this end, we have C sub fan. This is the C associated with the fan out of the signal. It might go to multiple different logic gates. It might fan out. So we'll group and lump all that capacitance together and call it C sub fan. Here's the wire. We said it's distributed R and a distributed C. So there's some unit R, some characteristic C, and some length of the wire. And then here's the internal capacitance of that logic gate here. So and then we have the resistance of the driver here, right? So that's the resistance of the pull-down network or the pull-down network of this logic gate here. So we have those R's, we know all the C's. We should be able to calculate what the delay would be to change the signal at the input of this logic gate in this situation. And I've spelled it out here. And it looks like a big thing, but it's actually pretty simple. It's just a bunch of RCs. What we have, and it's all a bunch of components that just add together because we can use superposition here because it's all linear. It's just R's and C's. Okay. So it's the propagation delay so the total propagation delay is going to be a sum of some terms. The first term is the resistance of the driver. That's the driving gate here, times its internal resistance, internal capacitance. Okay, so that's one term. Another term is the resistance of the driver times the capacitance, total capacitance of the wire, right? Then we're going to have this 0.38 times the wire resistance times the wire capacitance. That was from the previous slide. It's that term. Then we have 0.69 times the resistance of the driver times this capacitance. So it has to charge up that capacitance. Plus 0.69 times the resistance of the wire times the capacitance of the fan out. Right. So we're essentially looking at all the R's times all the C's and adding them all together. And so if you work it out, it ends up something like this. The resistance of the driver, 0.69 times the resistance of the driver times the internal capacitance plus the fan out, and 0.69 times the, we got this term here, which is the driver resistance times the capacitance of the wire plus the resistance of the wire times the fan out. This is all times L, right? Because C scales with L and R scales with L. And then you have the intrinsic delay of the wire itself. So it's not very pretty, but that's what it is. And if you ever need to know this, this would be a fairly accurate way to calculate this. And the CAD tools will do this in most circumstances because they understand, they have some internal model of the resistance of the driver. They know how to model wires for a given process, and they know what the input capacitance to logic gates would be. So the tools could calculate this for you, or you could do it manually if you wanted to. But I just thought you should see that's kind of the whole story then on logic gates connecting to other logic gates through wires. Okay, next topic. So I'm going to talk about some interesting cases that pop up. This is kind of a classic problem in VLSI design and chip design that comes up, is we need to occasionally drive very large capacitive loads. Right? Think about driving a clock node, a node on the chip that connects to many, many flip-flops. There's a lot of capacitance on that node. Or memory bit lines, or reset signals, or off-chip signals. If you have a signal on the chip and you're driving a pin, which is a bump, a solder bump that's driving to a circuit board, there's a huge amount of capacitance associated with that bump, or that pad as we call it, right? You have a little tiny inverter that needs to drive that signal off chip, right? So the inverter is tiny drive relative to the huge capacitance of the outside world, right? This comes up a lot. So you have a relatively small driver. If you just drove this out, this huge capacitance, whatever it is, maybe it's a connection to the outside the chip, it would take a really long time. The C would be large. There's a small amount of current. It would take a long time to develop enough voltage on that capacitance. So it would have a very slow rise time. And it wouldn't happen within one clock cycle or within the timing spec. So we need to do something to find a more efficient way to go from a small driving circuit to a large capacitance. The strategy is to use staged buffers. We do it in stages. Right? So the question is, how do we optimally scale the drivers? There's several questions here. One is, how many drivers do we need to get a minimal amount of delay? Right? If you put too many drivers in series, then you have a lot of logic. You accumulate a lot of internal delay because you have so many drivers. If you don't put enough, then you have a slow transition from one to the next. Right? So there's kind of a trade-off there. The other question we ask is, if you have a fixed number of drivers, let's somebody says, okay, we're going to do it in 3 stages. So what's the optimal scaling from one stage to the next? How do we make each stage bigger? At what rate do we make each stage bigger? And when I say bigger, I mean width. The width of the inverters, in this case, is the width of the transistors. Okay, so that's the problem. We're going to look at both of those, optimal number of stages and optimal scaling. First, we'll look at the simpler problem, which is the optimal scaling. Okay, so by the way, I think of this kind of as impedance matching, if you've seen this in other problems in engineering. It's kind of like in a trumpet. At the end of the horn of a trumpet, it doesn't just end the pipe there. The pipe flares out. This is to create a better impedance match, or a better match between the pressure wave inside the trumpet and the outside world. If the end of the trumpet ended without flaring out, it would generate very little sound because a lot of it would just get reflected back into the horn. It's a similar thing here. We kind of want to match the internal capacitance of the small inverter to the huge internal capacitance. So it makes sense we kind of flare up and gradually get bigger and bigger. Right? It's going to be, intuitively, it's going to be more efficient to do it that way. Okay, so driving large loads. So how many stages are needed to minimize delay, and how to size the inverters? Okay, so, and by the way, you may have thought of this, but to get the fastest delay, you could build just one really big inverter here, right? That would solve the problem, right? Because this inverter has a lot of output drive, has low resistance at its output, lots of low resistance driver, wide transistors, lots of current. Yes, that could charge, a big inverter here could charge that capacitor quickly, or discharge it. The problem we've created, this is not really the solution we want though, because in the process of making a really big inverter here, we've created a lot of input capacitance to this inverter, and somebody has to drive that. right? So we just kind of pushed the problem from driving a big output capacitance to driving a big input capacitance on this inverter. So we can't just solve it with a single inverter. So this optimization, first we're going to assume a fixed number of inverters. We know the size of the first inverter, and we know the size of the load that it needs to drive. So we're asking, what is the minimum delay of the inverter chain? What's the inverter? How do we size these in the chain, and what's the minimal delay that we can achieve? And again, remember, when we talk about size of an inverter or a gate, we refer to the width of the transistors, because the width is directly proportional to its internal resistance or its drive strength. So we can set up the problem this way. So we have n inverters. We have input capacitance. We're going to call that C sub G of 1, or C sub G1. That's the gate capacitance of inverter 1. We have output capacitance C sub L, like usual. We know from what we did a few minutes ago with this inverter delay calculations that the propagation delay of the jth inverter can be expressed this way. This was the intrinsic delay of the inverter times 1 plus the fan-out related part, which is the output capacitance of the inverter over its input capacitance. Remember, we had this as F before, or this is C sub L over C sub G before. Right? So this is gate capacitance of J plus 1 inverter over the gate capacitance of inverter J. Right? And there's a gamma there. Right? So this should look familiar. We just expressed it for the jth inverter. So the total delay of the chain then, remember we said we can kind of think of when we have a cascade of logic gates, we just add up the delay of each gate in the cascade. So the total propagation delay for this circuit is going to be the sum for j from 1 to n of the propagation delay of the jth gate. Right? We can factor out the t sub p0. They're all going to have that, t naught. And then, so we're going to have the sum of this, which is 1 plus c sub g, j plus 1 over gamma c sub g, j. And remember, the gate capacitance of the nth plus 1 inverter, which doesn't exist really, is just c sub l. That terminates this thing. So what's your intuition about how do we size what should this ratio be? I mean, we have freedom to size this. We could make this one small, and then this one big, and then this one small again, and that one big. Or we could do something else. But if you take my intuition like the trumpet, you want to slowly, one gets a little bigger, and then the next one gets a little bigger by the same fraction. Right? Next one gets bigger by the same fraction. So it's like a geometric expansion. Right? So each inverter should be scaled up by the same factor f with respect to the previous inverter. Intuition should show you that this is going to lead to the most optimal result, and it does. So that would make each stage have the same delay, because it had the same f in the delay equation, right? And therefore, given C sub the gate capacitance of the first inverter and the load capacitance, F should be the nth root of this ratio, right? The ratio between the two, the total output capacitance versus the input capacitance of the first inverter. We call that, by the way, F. That's big F. That's the total fan out that this chain is trying to drive. It's the ratio of the input capacitance of the first inverter under the load capacitance. And then if we want to distribute that F evenly through these stages, we're going to take the nth root of it. Right? So F is the total overall fan out of the circuit. So then if you believe this, we're going to fan out the same amount at each stage. So then the propagation delay for this will be n times the propagation delay of each stage. Each stage propagation delay is the same over n of those in series. So it would be just n times this. So here, that's the 1 plus nth root of f over gamma. Okay, so here's an example of a circuit like this. So let's say I say you have input capacitance of C1, output capacitance is 8 times C1. So it's this capacitance 8 times the input capacitance to that inverter. And I say you can only use 3 inverters here. What's the optimal F? What should F be? If this is a unit size inverter, and this is an inverter that's F times bigger, what should F be in order to make this work out? Well, there's 3 stages, right? So it should be the cube root of big F. Big F is 8. And what's the cube root of 8? 2. So it's 2 times 2. So this is size 1, that's size 2, that's size 4. And then the fan out for that one is from 4 to 8. So that's also a factor of 2 there. So at each stage, we're driving twice the capacitance that we had at our input. Right? So you can do that for any n and any f. Right? It's always just the nth root of f. Okay, so any questions on that? I'm going to move on to a more complicated problem now. Okay, this is also delay optimization. It's related, but now we're going to assume that we're given the size of the first inverter, we're given the size of the load that needs to be driven, and we're going to minimize the delay by finding the optimal number and sizes of gates. So now we have the freedom to use as many inverters in series that we want in order to minimize the delay. What I showed you before was to minimize a delay for a given number of inverters, but now we also have the degree of freedom of changing the number of inverters. Or, you know, same kind of logic works for, thinking works for logic gates as well. So what we need to do then is find an n. This was the formula, this was the result that we had on the last slide, right? Where this is the propagation delay through the series of n inverters. It was n times the intrinsic delay times 1 plus the nth root of f divided by gamma, where f was the total fan out for the circuit. What we want to do then is find n that minimizes this expression. Right. So here it is. And so we can do what we learned in, I guess, high school calculus. We could differentiate with respect to n and set equal to 0 and solve. And if you do that, you get this unfortunate result here, which is not very happy because f's on both sides. So f is equal to, and you can see it has a natural, because the differentiation brings natural log in, and then the solution ends up bringing an exponential in. So you get f is e to the 1 plus gamma over f. So there's no really simple closed form solution for this. There's only a closed form if you let gamma equal 0. What that means, letting gamma equal 0 means that we ignore all the internal capacitance of all the inverters. The drain capacitances are 0. Right? And when I learned design back in the 80s, that was the predominant model because the gate capacitances were so much higher than the drain capacitances. We just forgot about the drain capacitance and only considered gate capacitances. And so this was a really happy result. If you do let gamma equal 0, and then n is natural log of f, or the small f, the fan out per stage, is e, right? The base of natural logarithm, 2.71817? 2.71318? Oh, I always forget it. 2.7 is close enough. So that would mean scale up. If you could choose, so you choose n so that you scale up by this factor of e at each stage, and then let n be whatever, the closest n that matches as an integer. So that was kind of a cool result, but unfortunately, we can't ignore gamma. So it can kind of, you can plot things, or you can figure things out. I'll show you how we figure things out. So this shows a plot of, as a function of gamma, what the optimal f is. And we said gamma is close to 1. So for 1, optimal f would be 3.6. Here's another way to look at it. This is the delay in this cascaded arrangement of driving a large capacitive load as a function of f for different gammas. So if we pick our gamma of 1 here, we get this curve. This is from Dave Hodges' book. Dave was a professor here at Berkeley for many years, and he wrote one of the really good books on digital design. First, so what you see then is the optimal value is somewhere around here, around 4. All right. First of all, why the shape? So this looks like some kind of quadratic thing, right? It goes up when we go to the left, and it goes up when we go to the right. And why does that happen? Well, if the fan out is high, that means we're going to have a small number of stages in our delay chain, right? Because we're going to fan out. Each stage gets bigger at a fast rate. So to get from the small c up to the big C, we don't need many stages to do that. Right? As we increase f, the number of stages goes down. But what happens is the delay from stage to stage increases as we increase the f. Right? So that's why if you get to this point, it's not optimal because you don't have enough stages and you're trying to go increase the capacitance too quickly. Right? So the delay will suffer. If you go in this direction, you have less fan out per stage. The logic delay from stage to stage will be small, but you'll have a lot of stages in series, and their internal delays will accumulate. And so it'll slow down because they have too many stages. So there's some sweet spot. The sweet spot is kind of this minimal point here. Now, it turns out the curves are pretty flat for f greater than 2. Right? So it really doesn't matter. It's not very sensitive. As long as we're somewhere in this region, we're pretty optimal. Right? So in fact, it's common to choose 4. One nice consequence of 4 is it's an even number, and if these are inverters, you end up with the same logic inversion. If you used 5, you'd put a signal in, you get the inversion out at the output. If you want a non-inverting buffer, you'd build it with 4 stages or 6 stages so that you put a 1 in, you get a 1 out, you don't get a 0 out. Right? So you see this in the circuitry that's for driving pads. The circuitry that drives the signals that exit chips will have staged buffers, and they'll have something like 4 in series or maybe 6. Right? And this also, earlier, I guess last week, we were talking about FO4 delay, fan-out O4 delay. That's why that's an important number to look at, because when you're fanning signals out, oftentimes you do it with a fan-out of 4 and do it in multiple stages rather than doing it all at once, because 4 ends up being kind of a magic number for this fan-out delay optimization. Okay, so that's kind of an important result. And here's just another way to look at this. Here's this equation again, and what this is from Jan Rabai's book, and it looks at for different f's how effective this technique can be. This is unbuffered, so this is if you go just from a single inverter, what the delay would be. This is normalized to something, I don't know what, but you can see if you went up to this fan out to 10,000, you get a huge delay. If you use just 2 stages, it gets a lot better, but if you do this kind of optimal inverter chain, then you get a much better result. Right? And so the delay kind of goes somewhat logarithmically with the fan out, which is a nice, happy result. Okay, so any questions about this delay optimization stuff? Okay, so that concludes what I was going to say about timing. We have some more time, and so I'm going to start what's next. And what's next is a real disconnect. And the reason it is because we want to start talking about the RISC-V architecture, because those of you in the lab are going to be starting the projects pretty soon. And I wanted to start talking about this in class in plenty of time before the project spec gets released. So if you don't have a background in processors, you can learn what you need in order to get going on the project. So we're really going to shift gears. So we're going all the way from the circuit transistor level all the way up to the architecture level now and start talking about the RISC-V. So I'll just do a brief introduction today, and then next week we'll really get into it in much more detail. So give me a second. I'm going to switch to lecture 11. I think, yes. Gonna skip that for now. Okay, so what is RISC-V? So this is the fifth, so the 5 part means 5th generation. So RISC was if you don't have the history of this, RISC was the term that was coined here at Berkeley back in the 80s when researchers here were trying to figure out how to build microprocessors. In order to do it and make them efficient, they studied how to make them simpler. And one of the ways to make it simpler was to have fewer instructions. So RISC stands for Reduced Instruction Set Computer. It was in contrast to the computers of the day, which were complex instruction set computers. And now we take it for granted because most popular processors, except for the x86, which is a popular one, but most like ARM processors and lots of the embedded processors are RISC style. So this is our own version of RISC, and there were Berkeley RISC processors back in the 80s and 90s, and then this is kind of the latest generation, the 5th generation. The distinguishing characteristic of this is that it's a high quality, license-free, it's a free instruction set design that's free for anybody to use without royalties. And it's been experiencing rapid uptake or adoption in industry and academia. It's used by many universities for teaching and for research. It's starting to be used by lots of companies now. And there's a lot of software that supports it now, compilers and Linux ports, and so it makes it very useful. It's designed to be appropriate for all kinds of computing, from microcontrollers or embedded computers all the way to supercomputers. And because of that, there's variations on it. There's a 32-bit version, a 64-bit version, a 128-bit version. In the class, we're using a 32-bit version. The textbook uses 64. I don't know which textbook this is. This is probably a different textbook. I should say, if you've taken 61C here, you also know RISC-V, because that's what we use in 61C these days, as of a couple of years ago. We used to use a MIPS processor, which is kind of a competing instruction set. There's also now the standard, which started here in the computer science division here at Berkeley, now is maintained by a nonprofit, the RISC-V Foundation. You can find all kinds of details on this at riscv.org/specifications. It may come in handy for your lab work. And this is just to show you that there's lots of members now in this Foundation, the RISC-V Foundation. Lots of different companies are using RISC-V in one way or another. Some of them products, some of them just for internal development. This is just give you confidence that what we're teaching you here will be useful when you go out in industry, because there's lots of companies that are interested in RISC-V. And this list is growing all the time. So this is a real thing, even though its origin was here in academia. It's become an important part of industry work. Okay, so the RISC-V, really what it does is define not the processor itself, but the instruction set architecture. Okay, this is really the set of instructions that the processor executes. Right? So it's really the job of the CPU, or the central processing unit, also called a core, to execute instructions. That's really what it does. What a CPU is a piece of hardware, which is an engine that can execute instructions. By executing instructions, we can run software. Right? The nice thing about having an instruction set architecture, as we call it, that's the predefined set of instructions, it can be implemented many different ways. Okay, you're going to do an implementation in the lab, either on an FPGA or an ASIC. It will be different than somebody else's, but they'll all execute the same set of instructions, so they can all execute the same code. Right? This is a very powerful idea, because we can have different companies or different people building their own version of the processor. Some of them might be cheap and small, but relatively slow. Some might be bigger, more expensive, more powerful, hungry, but run faster. Right? So we can kind of serve different needs by the way we design the processor, but they all run the same software, right? Which is really kind of a powerful notion. That definition of what the software needs, the set of instructions, is the instruction set architecture. Since the picture is here, I should say, if you need more information on the processor organization, how do you build a processor that executes these instructions? Some of that you're going to figure out as part of the lab. Part of it I'm going to show you here, mainly next time and the time after that. But there's also a lot of information in this book, which is Dave Patterson and John Hennessy's book. And there's a version of it that's written using RISC-V for its examples, instead of the previous versions, which were written using MIPS. Dave Patterson, in case you don't know, is a faculty member here. He's retired now, but he still hangs around. He got famous by kind of inventing this RISC notion and writing the textbooks that use it, along with John Hennessy, who was a computer science professor over at Stanford and then chair of the department, and eventually president of the Stanford University. And now he's retired. Okay, so the instructions, these are the CPU's primitive operations. They're performed on simple processors, one after another in sequence. On more complicated processors of the type that you would learn about in CS 152 if you take that class, we can execute more than one instruction at it. We can start more than one instruction at a time. Each instruction does a small amount of work, a tiny part of the larger program. We'll talk about the various instructions here. Each instruction has an operation applied to operands, or the instruction either it affects operands, touches memory, moves something from memory into the processor, or from processor into memory, or it changes the sequence of instructions. Those are the branch or the jump instructions. Now, I said CPUs belong to families, each implementing their own set of instructions. So there's a whole family of RISC-V CPUs. So as I said, each CPU's particular set of instructions implements an instruction set architecture. There's other instruction set architectures out there. For instance, ARM, which you may have heard of, which are used in lots of portable and handheld devices. Many different ARM processors out there, but they all execute the same ARM instruction set. Same thing with Intel. x86 is its popular instruction set architecture. There's many different Intel processors the internal details are all different, but they all execute the same set of instructions. Therefore, you can move software from one Intel processor to another, and it should run. Same thing, there's the AMD is another company, and they build processors that also execute under license from Intel the x86 instructions. So you can move your software from your AMD-based computer server to your Intel-based computer server, and they all execute. The operating systems may be different, causing problems, but the base processors will be the same. So there's MIPS and RISC. These are the most popular, RISC-V. These are the most popular ones these days. MIPS not so popular anymore, it used to be. IBM, Motorola had their own PowerPC that was used in the old Mac, and it was used in some game consoles. There's an Intel IA64, which was a ill-fated instruction set architecture that never made it very far. And there's a long string of historical instruction set architectures that have moved on for one reason or another. And there's been sort of a consolidation of instruction set architectures. There's fewer these days than there used to be. So one nice thing about the RISC-V is it's relatively simple. We can put all the instructions on one page, unlike for the x86's many instructions. What this shows is, if you look on the right, so there's two columns of instructions here. The left-hand column has here the name of the instructions, and these are names that the computer doesn't know about. They're for human consumption. There's a instruction encoding for each type of instruction, as we'll talk about later. There's a set of arithmetic instructions like add and what else besides add? Subtract, and logical instructions like or and and. And then there's, as I mentioned, these instructions that change the flow of the program. The branch instructions are here, and the jump instructions. There's a few instructions down here that are mainly there to help the operating system or to help the coordination between parallel multiple cores. We're not going to talk about those in here. We're going to stick to the simple instructions. The other parts of these diagrams show the encoding. It shows how the instructions are encoded in a 32-bit word. We'll talk more about this next time, but we'll take a 32-bit word, which is the representation of an instruction as it is in the memory of the machine or in the instruction cache. And we assign a different interpretation to each field within the instruction depending on the instruction type. Part of some of the fields specify where the operands are, where they are in the register file, or give us information that we can use to compute the address of the operand that's in the memory in the case of the load and store instructions. And then, as I mentioned, part of the instruction encoding is a special code that tells us which instruction it actually is, right? So it's really the job of the CPU is to take each instruction word as it comes out of the instruction cache and decode it into a set of control signals that can be used to control the hardware to execute that instruction according to the definition of the instruction. And that includes setting the ALU to do the right operation, perhaps fetching the proper operands from the instruction file and presenting them to the input of the ALU, et cetera, et cetera. And we'll talk all about that when we get into details in the next few days. As I mentioned, this is not part of this class, those instructions. Okay, so let me just go a little more on this. So we can kind of help start to understand how to decode instructions for the RISC-V by looking at several different types of instructions. Each type really says how to interpret. If we identify what type of instruction is, then we know how to interpret the various fields of the instruction. Right? all the instructions are represented as 32 bits, but what each part of the 32-bit word means depends on what type of instruction it is. And we'll get into this later when we start looking at the details of how do we build a machine that interprets these instructions. Along with the definition of the instructions is part of the ISA really is the state that the program sees. And the state is the permanence or the memory that goes along with a running program. And in the case of the RISC-V, like most processors, there's a set of instructions, a set of registers, and the registers are the default operands for most of the instructions. Right. As we'll see, we like registers in processors because the register file is relatively small. It's a small memory block, which can be very close to the ALU, be right at the heart of the processor. And moving operands in and out of a register file can go very fast. So we can do that within one clock cycle. Whereas if we had to move operands from memory into the data path of the processor all the time, the whole machine would run slow because there's a long delay to get to the memory, partly because there's a lot of capacitance on the long wires getting to the memory, and the memory itself is very large and itself is very slow. So modern day processors use register files, and most of the operands for most of the instructions come from the register file with the result going back into the register file. So part of the RISC-V is that it includes 32 registers. Each one is 32 bits wide. 32 bits is the natural data width of the RISC-V instructions. So operands are 32 bits wide. Has register 0 through register 31. I'll review this again next time, but if you looked at the instruction encoding, the way we encode the instructions, there's an RS1 field and an RS2 field. This means the first register specified is specified in the instruction in the RS1 field. Second register, typically instructions have two operands, right? Like an add, you're adding two values together, producing a third. So it'll have two input operands and one output operand. So the right register destination is specified in that case by the RD field. So part of the instruction specification is an indicator which says which two registers to use for the input to this operation and which register to use for the output. Right? And if there's 32 registers here, that means we need 5 bits of register specifier for our S1, 5 bits for our S2, and 5 bits for RD, because 2 to the 5th is 32, and that lets us specify one of those 32 registers in each field here. A nice property of the RISC-V is that register 0, X0, as we call it, is always 0. So when you read it, you always get a 0. And when you write it, nothing happens. Right? This is built into the processor this way because 0 is a common, as we'll see, it's a common number that comes up. And in fact, this is a way to make an operation that does nothing, is you have that instruction write its result to register 0. It will have no effect on the state of the machine. It will be as if that instruction never executed. So it's a way to effectively make a no-op if we just want to have an instruction that does nothing. Right. So that's something to remember. The other part of the state, remember state is the same concept of state that I introduced earlier in the semester. It's just, it's some memory. It's something that has permanence from one instruction to the next. There's the program counter. This is a sort of a counter that counts through the program. You could also call it the instruction pointer. It's a pointer that points to the next instruction to be executed in memory. And it's probably in the instruction cache where it's coming from, but it's somewhere in the memory space. And then we have some memories. We have a memory that holds the instructions and the data in one 32-bit byte addressed memory space. Okay, so we can think of this memory as a long string of bytes. So RISC-V has byte addressing. Addresses are in terms of bytes, even though data items are 4 bytes and instructions are 4 bytes. We're going to use separate memories for instructions and data. Later, we'll replace these with instruction and data caches. But There's one big unified memory space, but the implementation will be the part of the memory space that's meant to hold instructions will be implemented as a I memory, and the part of the memory space that's meant to hold data will be implemented as the D memory, right, for the next couple of days. As I said later, we'll talk, in practice, these actually get implemented as in real processors as the instruction cache and the data cache. So instructions are read, fetched from the instruction memory. For now, we're going to assume that the instruction memory is read-only. From the point of view of the program, it's read-only because the program can't modify itself. It can't modify the instruction memory. Only the operating system can. So from the point of view of a running program, the instruction memory is just read-only. And then there's the instructions and the instruction set architecture. The instruction set has instructions for loading and storing the operands from the, not operands, loading and storing data from the data memory. So there's the load instruction that moves something from the data memory into the register file, and then the store instruction that moves a word from the register file back somewhere into the data memory. So the way software works on RISC processors is that variables from your program get mapped to memory locations. The ones that are going to be used for a while, the software will, the compiler will generate code that moves those operands into the register file as they're being worked on. And then when they're not needed after a while, the compiler then will move them back will generate code that moves them back to the data memory. This is to use the registers for the operands that are going to be used for a while, the most popular ones. Okay, one more slide. So this is the state elements. It just kind of summarizes it for the RISC-V. And this is important because if we think about the state, that tells us, gives us kind of the starting point for how to build a processor. Right? And what I'm going to do next time is really talk about how to build the processor from basic, just from looking at the characteristics and the functionality of the instruction set. But we have to start from the state. The state is, we're going to have a program counter. For that, we're going to have a register that every time we execute an instruction, we're going to increment the program counter to point to the next instruction in memory. Occasionally, we won't just increment it. We'll put a different value in it based on the branch instruction or the jump instruction. Right. We have the instruction memory that's going to hold the instructions. That's a read-only memory. You put an address in, you get data out. The data out, in this case, will be a 32-bit word that represents the next instruction or the instruction that we want to execute. The register file here, this is a collection of, you can think of it as a collection of registers, kind of like the homework we had. In this case, though, it's going to have an interesting property that we can read two different values at the same time. We'll call this a multi-ported register file. At the same time, on the same cycle, we can write a register. So it can read read two register values and write one register value all at the same time. If we can do that, they can make our processor very efficient. So this is kind of a special memory. We can do this because it's small. It's hard to do this kind of multi-porting on really large memories, but we can do it on register files. And then you'll have the data memory, which is a memory that has both read and write. You can read data out according to this word address. So you put a word address in, and data will appear on the output, the data that corresponds to that location in the memory. And then, that address will yield a corresponding data word. And this write address is used if we want to change the internal contents of the memory. You can write a word in by putting an address here, putting the write data here, waiting for the clock with the write enable, which is like a clock enable. That allows us to change some internal state of the memory. One last thing. For these state elements, the clock is used for write, but not for read. What we mean is there's asynchronous read and a synchronous write. So the writing happens, like in this register, or in the register file, or in the data memory, on the rising edge of the clock, if it's enabled to write. The reading happens asynchronously. It doesn't need a clock. if I put an address here, whatever that address is will kind of just ripple through and create some data at the output here. Right. Same thing with the instruction memory. There's no clock here because all we're ever doing is reading it. Change the input address and to point to some location in here. That location will magically appear at the output. Right? You can think of this as just a muxing operation. Right? The address is used to control a mux that muxes the proper value out to the output. There's no clock associated with the mux. It's just a combinational logic circuit. That's what makes it asynchronous. So asynchronous read, synchronous write. And that's an important property to get the high performance or the simplicity that we want. So we'll use that next time. Okay, so that's it. Brief introduction to RISC-V. Next time we'll kind of dive into how to build one of these things. So see you on Tuesday. Good luck with the homework. Have a good weekend.